Hello. Thank you to the organizers for inviting me. I am indeed Nathan Gibson from Oregon State University, and I'm going to be talking about a modeling method for dispersive electromagnetics and some numerical analysis results that follow from this particular approach. In particular, I'm going to talk about the Debye polarization model that's coupled to Maxwell's equations, and then a modification that in some sense fits data better, or at least seems more physically reasonable, and then a discretization method in random space, and then a discretization method in time, space-time, and numerical analysis results for the final fully discrete method. So this has been work that I started as a PhD student with H.T. Banks at NC State. I've worked with several other faculty and students over the years on various aspects related to electromagnetics and polynomial chaos and Debye. A lot of the work that's here is done with Vaishali Bokil, who some of you know, and I'll have references for various papers at the end. We've seen Maxwell's equation already today, Maxwell's equations. So this is the full Maxwell's equations with the time derivatives. The legend is at the bottom with the electric field, electric flux density, magnetic field, magnetic flux density. We have some sort of initial conditions and some sort of boundary conditions that aren't really going to be crucial in what I'm going to be talking about. I will say something more about the constitutive relations that close this particular system here. So the constitutive laws generally can be written as epsilon d equals epsilon e plus something, b equals mu h plus something else. That would be magnetization and polarization. For the current density, we have Ohm's law generally, which is another just linear heuristic, plus something else. In this case, that's a something special. That's a JS, such as the source term. And what we're thinking about in these problems is applications like pulse interrogation, cancer detection, defect detection, these types of things where you have some sort of source that's going into some sort of object, maybe out the other side, maybe reflected off, and then you take those measured electric field data, compare it to some simulation to do some inverse parameter estimation type problems. So what I'm going to be focusing on mostly today is the polarization, the choice of model that one uses for polarization, which might be appropriate for certain materials. I'm going to completely neglect the magnetization, although the techniques that I talk about would equally apply to magnetization models, and we have started looking at various magnetization models for other types of applications. The electric conductivity I'm also just going to sort of ignore, but you could leave it in there. It would just be along for the ride in what I'm going to say. But for example, for human tissue, the permittivity is much more important than the electric conductivity in applications. And as you'll see, the complex conductivity comes up anyway. So for polarization models and in some sense magnetization models, you can usually define these in terms of convolutions with the, in this case, electric field. So there's some sort of kernel, which is called the dielectric response function. The choice of that function and its parameters determine the type of dispersive model that you're choosing. It's probably easiest to think about it in the frequency domain, where when you convert this constitutive law epsilon e plus g star e, you can actually pull out the e hat and just call everything multiplying e hat an epsilon. I put the of omega in there to distinguish it from that constant epsilon on the previous slide, but I'm really going to be talking about this complex permittivity or frequency dependent permittivity epsilon of omega. Maybe I should point. So this epsilon of omega is the complex permittivity, and you can define your polarization model by just specifying what that thing happens to be. In particular, we're looking at pulse interrogation, which is inherently wide bandwidth, so we don't just want an accurate representation of some material at a particular frequency. We want accurate representations at wide ranges of frequencies, maybe specific wide ranges, but wide ranges nonetheless. And here's a picture of what I'm talking about. The blue is data, which you can tell because there are some sort of discrepancies there, call them errors if you like. And there are various competing models for trying to represent this data across various frequencies. The Debye model is what I'm going to be talking a lot about, but the Cole model is a competing approach which you can argue matches the data a little bit better in this case because the Debye seems to be a little bit too steep. And I'll just show quickly that that was the real part of that complex conductivity. The imaginary part is sometimes called the complex conductivity. This is governing the attenuation, the frequency-dependent attenuation, whereas the real part governs the frequency-dependent speed of propagation through these materials. And the specific forms for these models is given here. If you like to think in terms of the DRF, this is just an exponential with this relaxation time. So we've heard a previous speaker talk about tau being a relaxation time. That's what we have here. You can convert this convolution form into an ODE for the polarization, which is forced by the electric field, if you like, or you can think of it in terms of this type of complex permittivity. So back in the 30s, Cole and Cole looked at the real part versus the imaginary part on what's called a Cole-Cole plot, and data did not make these nice circles that this Debye model seem to imply. So they have this little fudge factor here that squashes it. So if you add some sort of alpha there, then this fits the data better. Unfortunately, now this does not correspond to a nice first-order linear ODE. It's a fractional order differential equation. Nonetheless, people try to simulate this thing. They've got lots of methods and theory about these methods. What I want to talk about is how we can have the simplicity of first-order linear ODEs and the accuracy of the Cole-Cole model. First, let me just show you a quick picture of what dispersion means. So when different frequencies are moving at different speeds, they sort of separate or sometimes clump up. So this is just a sine wave, it's a truncated sine wave, coming into a material. There's some reflection going off to the left, but this is what remains going through the material. You can see there's significant attenuation because the scale has changed in just 10 nanoseconds. But also there are these formation of these precursors here. And you would not get an accurate formation of these precursors if you were not representing that complex permittivity correctly over the full band of frequencies that's present in the signal that you're sending in. And if what you're trying to do is develop some guidelines for whether a signal going into your brain is safe or not, you want to be calculating the magnitude of these amplitudes here, not just looking at the stuff in the middle. So this is important to be able to measure accurately or to simulate accurately. So what we then do is we tack on the Debye model together with the Maxwell equations. You can see that there was a time derivative here, and I've just substituted in the ODE, the Debye ODE up in here, so it looks like there's an extra term times E, which you would have gotten from Ohm's law anyway, which is why I'm suggesting that that's kind of redundant. But you also have the polarization entering directly into Maxwell's equations. So one of the things that I'm going to be talking about is the dispersion relation of the continuous system as well as the discrete system, because we want to make sure that we are accurately simulating dispersive waves. We want to make sure that the dispersion relation is being matched by the discretization. So first we need to specify the continuous, the true exact dispersion relation for the Maxwell-Debye system, which is given here. This is the wave vector. C is the speed of light, which is this guy right here. And then the complex permittivity is basically, in some sense, scaling that speed of light. For Debye model, it's this. If you choose a different model, then the complex permittivity just enters right there. And I should say that the way to visualize the epsilon infinity is that it is the limit in the infinite frequency case of this real part of the permittivity, and the epsilon d is this jump from this plateau to this plateau right here. And this omega tau business here suggests that omega equal 1 over tau has some sort of significance, and omega equals 1 over tau is where the jump is occurring. So what we're really doing with this Debye model is saying, where is there a jump? Okay. And for the notation of what's to come, it's actually a little bit easier to write things in terms of two spatial dimensions. So I'm going to assume that there's no variation in the z direction, and that decouples this into a transverse electric and transverse magnetic systems. I'm choosing to look at just the transverse electric, which is defined here in terms of an electric field that has an x and y component, a magnetic field that only has a z component, so it's not bold. Polarization is an ODE that's forced by the electric field, so it's in the same type of space as the electric field is. And now I have to interpret this curl as a scalar curl, which is defined here, and this curl as a vector curl, which is defined here. Okay, so that's the notation that I'm using from here out. And then Ji-Chun Lee proved in 2010 that the system is well posed, and in particular, this was the crux of the work to show that there's some energy of this system that involves an appropriate norm of the magnetic field, an appropriate norm of electric field, and also polarization, so that there is energy decay in this case. It's not energy conservation because this is dissipative, so it's energy decay. And we're going to compare to this result as we go through discrete versions of this discretizations of the Maxwell-Debye model. So first, the argument of why we want to improve on the Debye model. So I've already mentioned that the Kokol model is a fractional order. Debye is efficient but does not represent the permittivity well. And it's been known for some time that there should be a distribution of relaxation times. In fact, before Debye wrote down his version of the model for this, it was hypothesized that there should be a distribution of relaxation times in most materials, because most materials are essentially like mixtures, or there's some randomness inherently in these materials. And when they've done measurements, they've been able to see something that looks maybe like not quite Gaussian, but beta distribution of relaxation times for things like water. The other way of thinking about it is that the Debye model was too steep of a jump, and if you want a more gradual jump, you take a few jumps, and you get a stair-step approximation to a slanted line. And it's not a finite number, although people do that. There are many performance codes that just say, okay, Debye's not good, so we'll use 4 poles of Debye, and we'll run that because that's very efficient, but it's not as accurate as what we're going to talk about here, because this is a continuous distribution of these Debye jumps. All right, so here's a quick picture that some undergraduates did in 2008, where they just fit the model that I'm going to show you that employs a distribution, in this case simple uniform distribution of relaxation times, and just try to match the data and see if you can beat Kokol. And the eyeball norm suggests that that's not terribly bad. quantitatively, okay, Kokol's still beating us, but you see that it's less steep than Debye. Okay, so that this is really showing, at least in the case of dry skin, permittivity measurements that we can accurately model the complex permittivity of measured data with a distribution of relaxation times in the Debye model. Okay, so mathematically what that means is that instead of having just one parameter set Q, so for the Debye model, think of Q as having that epsilon d jump and the tau, which tells you where the jump happens. You actually have a distribution of those parameters. So then when you talk about polarization, polarization really means the macroscopic average of the dipole moments, and what we mean now by that is it's the expected value of these of the convolution. Okay, so another way of thinking about that is that you could just define tau as if it were a random variable, which implies that the solution to the ODE is now a random function. So I call this script P the random polarization, and the macroscopic polarization is expected value of the random polarization. Okay. I'm really thinking of this as like a multi-scale averaging model. So now the Maxwell system only sees the macroscopic polarization, which is the expected value of the random polarization, but the random polarization is a random ODE. This is a random ordinary differential equation which is forced by a deterministic electric field. This is not random Maxwell's equations. I know some people have done random epsilon infinity, and that makes the electric field random, and then you have to worry about the entire PDE being random. That's not what I'm doing at all. I still have a deterministic Maxwell system. I just have a random ODE here, which is involved somehow in forcing that Maxwell system. So here are just some example of results of what one could do with this. If you're doing a parameter estimation type problem, for example, trying to find the relaxation time for a particular material, you take your data, you do the usual thing with the least squares, regularized least squares, the Gauss-Newton. That's exactly what we did here. But instead of finding a single relaxation time, I want to find the range of relaxation times, or in this case, the distribution of relaxation times that happens to be present in the material through which my pulse went in order to generate the observed data. And the blue thing here is my initial guess of what that distribution might be. And underneath this guy somewhere is the true solution. So we have very good convergence here. And here's my data fit in case anybody asks me. So there's data here. This is artificial. It's a toy problem. We threw some noise on there to make it horrible looking. But that's what that's what the initial guess would look like. And then Gauss-Newton gets it down to a pretty good match here. Okay. That's just what hopefully one would want to take away from why are we doing this, is because if you have a material that actually is modeled or exhibits multiple relaxation times, you should be searching for all of them, not just the mean value of them. So now we want to look at the dispersion relation for this system so that when we do a discretization of this Maxwell random Debye model, we can see whether our discretization is matching the dispersion relation for this, which I'm going to be calling the true system. So the only thing that really changes here is that the complex permittivity now is an expected value because it involves a random tau, and it's not 1 over 1 plus I omega expected value of tau. It's the expected value of this, and it's really just algebra to show that that's true. But just sort of as a curiosity, it turns out that if you have a uniform distribution, there's an analytical form for this, and that's what the REU students were able to just plug in find the best tau A and tau B rather that fits this fits that dry skin data. So there is a proof, and it's a very boring proof. And the same thing happens in 1 and 3 dimensions. But again, the point is that I'm going to be comparing this to the discrete dispersion relation to make sure that we have accurate representation of the dispersion over all frequencies. Okay. So in order to do the next part, which is compared to the stability result from Lee, I need to introduce Hilbert spaces that allow me to have this random variable in there. You can call them a random Hilbert space. Omega is sort of the random space, and then D is the X and Y physical space here. So we need an inner product, and we need a norm, which is actually just the expected value of the L2 inner product and the expected value of the L2 norm. And in this context, we can write out the weak form of the 2D version of Maxwell's. This, again, is the transverse electric, but with a random Debye. So you see the random Debye is right there. And we can say that we have stability because we are able to find an energy. Same thing for magnetic field, same thing for electric field, but now this is a random polarization. So we need this notion of a norm on this random Hilbert space. But it turns out that it's basically the exact same norm that we had for the deterministic polarization. It's probably not surprising, but it took me a while to figure that out. So I'll just say that there are some details in here, and the scalar curl adjoint with the vector curl, where was it? Maybe that's coming later. Yeah, that's later. Okay, so these things, those two cancel out. These guys add together to be a square of something. And that's the derivative of E squared, so the derivative of E is actually negative. That's what you need to know from this. And it's the same proof that Ji-Chin Lee did, except we just have a different norm now. So now that we have a random ordinary differential equation coupled with Maxwell's, we need a way of solving this random ordinary differential equation. We only need to extract the expected value out of it, so you could just do a quadrature rule, but polynomial chaos seems to be popular these days, so we'll talk about that. If we think of the random relaxation time as being in terms of some sort of fundamental random variable, a germ, maybe that's mean 0 and variance 1, for example, then you can think of the scaling and shifting parameters as like a radius and a middle of the interval that we're talking about here. And then nice things happen in the polynomial chaos context. The vector of coefficients of the polynomial chaos expansion of the random polarization satisfies a linear ODE of the same form, but now this is a system. The M is the Jacobi matrix corresponding to the orthogonal polynomials that are orthogonal with respect to the PDF of the distribution that you decided to choose. And there's this plus Tm business here. This is tridiagonal. This is very easy to solve. And the whole thing is still forced by the electric field, but only in the first component. Everything else is zeros below that. Okay. So you end up with this type of tridiagonal first-order linear system that you would have to solve. And again, from what you want to extract out of this is just the zeroth, or the first component, first element of the alpha vector, because it's the first element of the alpha vector that is actually approximating the expected value of the random polarization here. And just for your benefit, we know that the eigenvalues of the Jacobi matrices are inside the support of the random variable, which I chose to be -1 to 1. Therefore, we know that that A matrix happens to be positive definite because the radius is less than the middle. I'm not allowing 0 to be a possible relaxation time. You may be wondering, how big would A need to be realistically? Here's just a quick little convergence result that some other undergraduates had done to show that really 4, and this is from 0 to 4, so it's a 5 by 5 matrix, is reasonable to get to a ridiculously low error for a moderately wide distribution. Moderately wide meaning 25% on either side of the value of the mean or the middle relaxation time. So we're thinking between 5 and 10, between 5 by 5 or 10 by 10 is how big A is. Again, it's tridiagonal, so it's cheap compared to the PDE. It's not that big of a deal. The 2D Maxwell, now polynomial chaos Debye instead of random Debye model looks like this. There's an alpha 0 of x component for the EX equation, alpha 0 y component for the EY equation. And we have the same A here, so you can do your LU factorizations at the beginning before you do your time stepping. And there's the alpha x component and the alpha y. And just for notation later, I'm going to boldface the alpha vector. It's a vector in the sense that it's a collection of coefficients in the polynomial chaos expansion. It's bold because there's an x component and a y component, just like E has an x component and a y component. All right, so the choice of time discretization or spatial discretization is sort of arbitrary. The whole point of wanting to do the random Debye and the polynomial chaos is to make things as efficient as possible. So in that vein, I'm looking first at finite difference time domain. So it's finite differences in time, finite differences in space. In particular, we're using a modified version of the Yee scheme developed in '66. Three-dimensional, but we're only using the 2D version that I'm talking about right here. But the point is that it's a staggered grid. So the H is staggered from the E in both space and time. That's the important part. And because of this, it ends up being second order accurate. Okay. So the original Yee scheme was not for dispersive media. We would have to modify that. So I'll have to tell you what that is. But just the properties of Yee scheme is that it's conditionally stable if you have this type of usual CFL condition. It's well posed. It does exhibit its own numerical dispersion. The dispersion here then needs to be roughly close to the dispersion in the actual true solution because the media itself is dispersive. And then we also have some dispersion error introduced by the polynomial chaos. So we have lots of contributors to dispersion. The point is that they somehow need to match the true dispersion. So in order to do second order in space and time scheme for Maxwell's equation with some sort of polarization model, you need to have second order in time discretization for the ODE. The polarization model does not have spatial derivatives in it, so we're going to use second order center differences. We're going to average the zero order terms. It turns out when you're doing this that you keep the CFL condition with the caveat that the speed in the CFL is now the maximum speed that's present in your dispersive material because they don't all travel at the same speed, of course. And this is what it would look like if, for example, I did a 1D system and I did the staggered space and time for the H equation, for the E equation, and then I did centered differences here for the polarization, but I did the averaging of the zero order terms. So that's what I'm talking about doing. This is what 1D would look like, but I'm doing everything in 2D here. So it's known, Peter Petropoulos showed in '94, that the discrete dispersion relation, this is the dispersion relation for the Yee scheme when applied to the Debye model, has this form here. I'll come back to the K, but the epsilon delta is basically a discrete approximation of the true epsilon of omega. And it's an approximation in the sense that the omega is approximated and also the tau is approximated. And this is what they are approximated by. And you can see clearly that if you reduce the time step, that you get better and better approximations. Okay. This K business here is related to the symbol of discrete first order difference operator in this way. So in some sense, the the stuff that's happening on the right-hand side is independent of your polarization model. It's independent of your time discretization. It's completely separate. It's determined by the choice of spatial discretization that you happen to use. So, for example, we looked at what happens if, instead of using second-order finite difference on spatial derivatives, you used arbitrary even-order spatial derivatives. You can come up with what this k looks like, and this thing stays exactly the same with the new k. You can also look at 3 dimensions instead of 1 dimension or 2 dimensions. The left-hand side stays exactly the same. So you can construct your discrete dispersion relations by just plugging in the pieces of the choice of time or space discretization that you use. So if we're going to be doing the polynomial chaos system instead of the Debye system, we still need to do second-order accurate center differences. So I just show you what that looks like. There's nothing special here. That's just how you have to do it. And what I want to do now is then say something about this fully discrete method. So I've discretized in random space with polynomial chaos, so that's pseudospectral and random space. Finite difference in time and space. What are the stability results for this? I need new norms now. So these are grid norms here. So I have a grid norm basically for E vectors, and I have a grid norm for basically H vectors. And I'm going to borrow the E grid norm in order to define my alpha grid norm, in the sense that it's just going to be the sum of the 2 norms of each of the elements of these alpha vectors. Okay. And then there's a corresponding inner product that we'll also be using in order to be able to say, finally, that there exists an energy, this is now a discrete energy, that looks a lot like the discrete energy for the Debye case, but now this is for the polynomial chaos case, in terms of this newly defined alpha vector business here, so that we can say that this energy decays from one time step to the next, and that gives us our stability. Okay. And although, again, it looks like it's the obvious thing to do, it didn't seem obvious when I was going through the motions, and one thing that I would like to point out is that it's the random Debye norm had this F norm of the random polarization, which means the expected value of the 2 norm. That's the way we defined the F norm in the first place. And it's well known that the expected value of something squared is the square of that plus the variance. And it turns out that the alpha 0 is the thing that approximates the expected value, and it's the sum of the squared of everything else in the alpha vector that approximates the variance. So when you add those 2 things together, you get exactly the alpha norm of the alpha vector. So the alpha norm of the alpha vector, the way this has been defined, is exactly what you need to approximate the F norm of the random polarization. So had I known that at the beginning, this would have taken me 5 minutes to prove, but there it is. Okay, so and there's some details of the proof, but it's exactly the same as what we talked about before, and it really follows the deterministic case, which is in this 2014 paper. And I guess I should say, since I mentioned that A is positive definite, that's where this actually gets used. I hadn't used it before, but it's important right here. So that was the stability result for the fully discrete. This is the dispersion result for the fully discrete. So the discrete dispersion relation looks exactly the same as what it would for Yi-scheme for Debye, except that now epsilon delta is supposed to be approximated by a mega delta, which is a misrepresentation of the frequency. In this case, that's exactly the same as the Debye case. It's the same omega delta. And we're supposed to have a tau delta here if this were the deterministic version, but it's not. So we have an A delta. but the A delta is exactly the same as what the tau delta used to be, except there's an A there instead of a tau. And again, A is that scaling of the Jacobi matrix from the polynomial chaos. Since this is a matrix, you have to, and instead of having 1 over 1 plus I omega tau, we have to have the matrix version of that, so the inverse of I plus I omega tau. And we also need a scalar representation of the complex permittivity. So this is taking the 1,1 element of this inverse to be the representation of that 1 over 1 plus I omega tau. And here, for comparison, was the previous version. So there exists a proof of that, and I'll just say that after you do the plane wave substitution, everything's just really, really horrible algebra. But you get down to the point where this is exactly what I said on the previous slide. This is the sketch of what it would look like for 1D, but it's exactly the same for 2 and 3D, obviously. All right. So now that we have a discrete dispersion relation, we can compare this to the true dispersion relation, which in this case is from the Maxwell random Debye. And what we're going to do is look at errors, in particular relative errors. And we're looking at relative errors in terms of K. So what I mean by that is, given a dispersion relation, remember the K is buried inside of here, solve for that little k for the true model, the exact dispersion relation, and this discrete dispersion relation, and then take the relative error there. It's clearly a function of omega, but it's also a function of delta t. And for convenience, I'm going to show plots of that phase error as a function of omega times delta t. So in your mind, you can fix delta t and move along the omega axis, or fix omega and move along the delta t axis, if you like. I'm choosing these particular parameters just because this is similar to what water would look like, except I'm using a rather broad distribution, 50% on either side of the relaxation time for my distribution. And this is just for uniform distribution, but honestly, the beta looks almost the same. So these are the phase error plots as a function of omega delta t. And this is showing us a couple things. The first thing that probably pops out is the blue curve is horrible compared to what the other things seem to be wanting to do. And the blue curve is if you did not have any randomness in your system. If the true material actually has a distribution of relaxation times, but you're pretending that it doesn't because you're just using the mean value of the relaxation time, that's how bad your dispersion is going to be. The rest of these curves are including just one term of polynomial chaos, or two terms of polynomial chaos, or three terms of polynomial chaos. And in the sense of that 50% on either side of the mean value of tau, 3 is probably all you really need. If you did 90%, which is like insane, you would need 6 terms, but still that's tiny. That's much less than the 10 that I quoted you before anyway. And I should be honest about one thing. I fixed the delta t to be the mean value of tau over 100 for generating these plots. So your eye should really just be focused down here for the actual effective dispersion in the frequencies that we care about. And I should have mentioned near the beginning that we care about frequencies that look like 1 over tau because that's where that jump is happening. If you're using this in some sort of inverse problem to figure out what material you have, the greatest contrast between two different materials is where that jump is happening. So we really care about what's happening in the neighborhood of omega equals roughly 1 over tau. So this is the dispersion that we're looking at down here. If I were to decrease the sort of baseline time step, you can see that this thing goes to 0 much faster here, much faster here. Same story with the number of terms that you would need to use. This is the 2D version of it in the sense that I've now fixed omega equal to 1 over tau. So we are only now looking at that frequency that is most important in some sense. But we're looking at what does the dispersion look like from different angles. And what you can see here is that if you did not include randomness when you should have, your 2 orders of magnitude, this is a log scale. It's radial, but it's a log scale. 2 orders of magnitude off from the true dispersion. And you would only just need to have a 4x4 matrix really to have gotten the best dispersion that you could have gotten with that choice of time step. If you decrease the time step even further, then of course you decrease the best that you could do, but that's not realizable unless of course you're using at least a 4x4 matrix in the polynomial chaos. Conclusions. So what I've talked about hopefully is the need for a random ordinary differential equation, but also what you could do if you had one. In particular, the pseudospectral discretization in random space, and then some sort of time and space discretization. The thing that I like about this not only are the simulations very fast, but the numerical analysis flows nicely throughout. And in general, you get to take advantage of the fact that the polynomial chaos exhibits this exponential convergence rate in terms of the number of degree of the polynomial chaos expansion. And these are the references, and in particular, almost everything that I talked about was in this last little thing, and I believe there's a preprint on my website because it's slow coming out. Yes. Okay. Yes. So the second one I have looked at the second one, and you can show that it's exactly what I just did. In a loose sense, that if the parameters of your distribution are the best you can do to approximate the Kolcol model, and you do the polynomial chaos discretization of that random relaxation time, then you're doing exactly a quadrature on the Kolcol model. Those are exactly the same. And I think Petropoulos had done that, and we compared our results to his. I actually haven't looked at stretched exponential before, so I will.